Hello guys, today we will talk about the principle behind most of the statistical test. To show the principle, I will show how the one sample z-test for proportions makes the inference. For that, let's take one exercise on one sample z-test for proportion. A survey claims that 9 out of 10 doctors prescribe aspirin for their patients with headache. To test this claim, a random sample of 100 patients with headache is obtained. Of these 100 patients, 82 indicate that they were receiving aspirin. Is the claim that 9 out of 10 doctors prescribe aspirin for their headache accurate? Let's assume that the claim is correct. Let's assume the total population in a city of people with headache who have visited doctor is 50,000. So out of those 45,000 will be receiving aspirin. That is 9 by 10 of the total populations. So let's first go to the data that I have here. This data sheet contains of 50,000 patients. Since the first patient ID is 0 and the last patient ID is 49,999, we have total of 50,000 patients. Among them, some are receiving aspirin and some are not receiving aspirin. Let's first calculate the number of patients receiving aspirin. That will be equal to count if C2 ranging to C50,001. So 45,000 patients out of total 50,000 patients are receiving aspirin. So 5,000 patients are not receiving aspirin. So this is a total population of patient. Now let's go to Google Colab and first update the data here. So we will upload the data. So I have just shown in Excel here. The data will be uploaded here in a few minutes. It is uploaded here as zprobe test data. Now I'll have to read this data in a coding cell here. To understand what I am trying to show you today, you don't need knowledge of Python coding. So please follow along with me. So first we read the data here in a coding cell, and after we have read the data, we can see the data here. So data has been uploaded here. We can look for the total number of patients in our data sets, that is 50,000. Now we will first select random sample of 100 people from those 50,000 people. This is the first random sample of 100 people from those 50,000 people. So here we have 100 patients which has been selected randomly. This is our first samples. We can also select a second sample randomly. And this is our second sample again containing 100 patients. If we look closely, the first random sample is completely different from second random sample. Now we can see how many number of patients in first sample is receiving aspirin, and that is 86. People in first sample are receiving aspirin. We can also see how many number of patients are receiving aspirin in second sample, and that is 91. So the proportion of people receiving aspirin in first sample is 0.86, and the proportion of people receiving aspirin in second sample is 0.91. Next, we look at the formula for the G statistics. G is equal to sample proportion minus population proportions, that is divided by square root of population proportions, multiplying that by 1 minus population proportions and dividing by n, and all of the denominator is in square root. Let's first deal with the denominator part, and this is also known as margin of error. So margin of error is square root of population proportion multiplied by population proportions multiplied by 1 minus population proportions, which is 0.90, and we have to divide that by number of sample, which is 100. So the margin of error is 0.03. Now we can calculate the statistic for the first sample, which is equal to first sample proportions, which is equal to 0.86 minus population proportions, which is 0.90, divided by margin of error, and that is minus 1.333 as the G statistics. Similarly, we can calculate G statistics for the second sample. The second sample proportion is 0.91 minus sample proportion 0.90 divided by 0.03. So the statistics for the second sample is 0.333. We have calculated the G statistics for the two sample above. We can similarly calculate the G statistics for 10,000 randomly selected sample. Each sample will contain 100 patients, and total 10,000 randomly selected sample will be selected. Since there are many samples, almost 10,000, it will take some time to calculate the G statistics value. After these calculations, we will get total 10,000 G statistics value. We will plot these 10,000 G statistics value and see that most of the G statistics are between -2 and +2. This list 3 contains the G statistics value, and the total number of G statistics value are 10,000. These G statistics are for 10,000 randomly selected samples, with each sample containing 100 patients. This is a long list of G statistics for the sample. Now let's see what proportion of the statistics value are between an arbitrary value -1.96 and +1.96 out of those 10,000 statistics value. We see that total 9,370 patients, no, it is 9,370 samples has G statistics value between -1.96 and +1.96. That is 93.7% of samples has G statistics between 1.96 positive and -1.96. So we can safely say whenever we select a sample of 100 people from the total populations, then calculate the proportion of patients receiving a aspirin, and then calculate G statistic assuming sample proportion is 0.90, then G statistics values are within minus 1.96 and plus 1.96, 93.7% of the time. Now let's go back to Google Slides, and for this exercise, the null hypothesis is that population proportion is 0.90, and alternate hypothesis is that population proportion is something else than 0.90. For these samples, there were 82 patients which were receiving aspirin. So sample proportion is 0.82, sample size is 100, and G statistics is minus 2.667. Now we know 93.7% of times the G statistic is between plus 1.96 and minus 1.96 when we select the samples randomly from the populations. Here the G statistics for the sample is minus 2.667. The probability of having such G statistics randomly is below 6.5%. It is in fact 0.005%. We can go back to Google Colab and see that here in a coding cell. Here we are trying to calculate among those 10,000 G statistics value how many number and how much proportions are equal to 2.667 or more negative than 2.667. And we see that 0.0043 percentage of G statistics value are equal or more negative than 2.667. So the probability of having such a G statistics by random chance is very low. We say that this G statistic was not achieved randomly at 93.5% level of confidence. So we conclude that the statistic of minus 2.667 was achieved because population proportion is something other than 0.90. So we conclude that the claim population proportion is 0.90 is inaccurate. To conclude, we don't believe on randomness when the probability is low. This is the theme behind most of the statistics. Believe me, you will thank me if you will remember this idea for a long time. Lastly, though, we found that 93.5% of the samples had G statistics between minus 1.96 and plus 1.96. G distribution assumes that 95% of the samples had G statistics between that range. If we take a larger population above 1 lakh, then we will see that 95% of the samples will have G statistics between minus 1.96 and plus 1.96. This video I showed how G statistic is used to test for proportions. The same principle applies to T statistics in t-test, chi-square statistics in chi-square test, and many other such tests. I will provide the link for the Google Colab and the dataset in the GitHub. The GitHub link will be provided here with the video. Please go and check for yourself that the demonstration shown here is true. Thank you. Like and subscribe.